Hi guys, this video is an overview on iterators in C++. This gets the big ideas across. We'll go into the details in later videos. When the C++ designers invented iterators, they were trying to solve some particular problems in the language. One problem is to model the concept of a location inside a container. Down here, this cloud represents some kind of abstract data structure. Maybe it's a vector, maybe it's a linked list, maybe it's something else. And we have a need in programming to represent one location inside there. And that's basically what an iterator does. It represents a location inside of another data structure. For example, this iterator is pointing at the 4, so it represents the location where the 4 is. And you might be accustomed to an index inside an array. That's a similar concept. The array is one object, and the int index is a second object. That int index represents a location inside of an array. Compatible with object-oriented programming, there are two design goals that they had. One is abstraction. The abstraction ideal is that client code should be unaware of implementation details. So if I use a vector and a vector iterator, I should not have to know about details like what kind of pointer is used to store the elements. Or if I'm using a linked list, I shouldn't have to know necessarily whether it's a singly linked list or a doubly linked list. I should be able to just have a list and a location inside of a list. There's also the goal of encapsulation. That's the goal that client code can only interact through a defined public interface. In C++, that's the public member functions. We don't want client code to be able to go in and mess around with private data members because for one thing, the client code could break them somehow, and for another, it makes the code tightly coupled or brittle, meaning that if we ever change how a data structure is implemented, it will break a whole bunch of client code. It won't compile anymore. And we achieve this, for example, by allowing you to call the front function that returns the first element in a data structure, but we don't let you access the head pointer in a linked list because the head pointer is a private implementation data member. Here were the use cases that iterators aim to solve. So this is what we want iterators to be able to do. I think going through this explains why they're designed the way they are. One is to be able to loop through elements. We've got these data structures that contain elements, and we'd like to be able to loop through them, maybe to print them out or to put them in another data structure or implement some algorithm that involves visiting all the elements. Some data structures allow us to loop both forward and backward, so we'd like that to be possible. It's easy to iterate backward through a doubly linked list or an array, so we don't want to lose that freedom. We want to be able to represent where to add or remove an element. Let's say I want to remove that 4. An iterator could represent the location of where the 4 is, and then that would be a way I could say remove the element at this location. We could also say add an element at that location. We also sometimes want to add or remove multiple elements. Maybe I've got a collection of 8 numbers and I want to stick them all into this data structure at this spot. So we need a way of representing a series or range of a few elements that all go into one location. We do that with 2 iterators. We'll get into that soon. Similarly, we might want to be able to pass multiple elements to a function. Let's say I wanted to send half of these numbers into some function. One way I could do that is to make a new data structure and copy half of them over, but that's a relatively expensive big O of n operation. Instead, maybe I'd like to be able to say just this function, I want you to start here and here. Those are the elements you operate on. Finally, we use iterators as a search result. Sometimes we search for something in a collection and it may or may not be present. So if I wanted to search for an even number, I might find this 4. So that's a location, valid location, we found it. But what if I search for the number 9? 9 is not present. So we want iterators to be able to represent that idea of not present. I couldn't find it, not found. So the solution is these iterator data types. Every container data type has a corresponding iterator type. They are usually nested classes. You can actually put one class inside of another class, and you use the double colon operator to distinguish them. So for example, std vector is the familiar vector class. Std : vector : iterator is another class that is an iterator into a vector. And likewise, standard list has standard list iterator. Standard list iterator is a location within a standard list, and so on. That's true for the other collection types. For legacy reasons, in order to make this iterator scheme familiar to experienced C++ programmers, a raw array has an iterator type of a pointer into that array. So if T is a data type, T star is an array, then a T star raw pointer counts as an iterator. We'll get into that in the next video. The abstraction goal is achieved because all of the operators use the same operators in order to move through a data structure. We use the plus plus operator, dereference star operator, the comparison operator. That's what we use for all of these iterator types, regardless of how they actually work internally. And the encapsulation goal is met. The client code still can't see private data members. If you want to represent a location inside a vector, you use a standard vector iterator. That lets you achieve that goal of representing a location, but it does not let you see any of the private data members of vector. Now, vectors or iterators can represent a past the end idea. An iterator is always in one of two states. It's either at a valid location. For example, this red arrow represents an iterator at the location of the 4. That is a valid location where an element actually is. Or an iterator can be in a past the end state. That would mean the iterator is pointing at this region to the right of all of the elements. There's no elements there anymore. The rationale is to be consistent with the conventional idiomatic for loop in C++. And the way that that for loop works is you start at the beginning, and as long as I'm still at a valid location, we do something in the body of the loop, I++ to move to the next index. That last I++ moves I to become equal to n, and I equal to n is not actually a valid location in an array. So to make this kind of loop work with an iterator, it needs to be possible for an iterator to move through all of the valid elements and then move past that to past the end, not a location where an element is anymore. We can represent a collection of elements inside of a data structure as a range between two iterators. So now using two separate iterators, we can represent a beginning or a start with S and an end with E. So these two iterators are representing start at 1, end at 5, and that represents the range of 1 through 5. Now, there's a convention that when we set up one of these ranges, the set of elements includes the start, but does not include the end. This is the math notation for that kind of range, like a range of numbers on the number line. So in this example over here, starting at 1, ending at 5 means include 1, 4, 6, but not 5, not including the end. It's a little bit unusual, but there are some good reasons for this. It makes more sense once you see how iterators are used in the library. For one thing, this makes it possible to represent an empty range. If the start and end are the same location, the not including the end rule means that that represents no elements at all. So if I have the start pointing at location 1 and end also points at location 1, that actually means no elements at all, an empty range. So that's one rationale for this convention. It makes it possible to represent an empty range, which is a convenient thing to do sometimes. And it does make those for loops more idiomatic. We'll get into that in a later